Okay, good morning, everybody.
Morning.
Morning.
Good morning.
Good morning.
We'll get started. I think everybody is here who's going to be here. Alana told me she's not going to be here. We got Alex. I see Justin and Maroon. Oh, we got Canterbury. I don't see Canterbury. Are they here? No. They must be running a little late. Okay. Let me just begin by restating some announcements. Okay, so as you know, this is our last time together today. Kind of sad, but you have one more thing to do after class today, which is your final test. Okay, and as we said on Tuesday, your normal point person at your school is in possession of your last test, and you can take it at your convenience during any 1 hour period between the end of this class today and next Friday, and mid-afternoon next Friday. So not, or I would like to try to get everything graded and even returned to you with the final grade by the end of the day Friday. So I'm hoping that no one wants to take the exam like at 4 o'clock Friday afternoon. Okay, I would rather you take it early. And as I said, also on Tuesday, we have a homework assignment that is due today. It kind of is extra. We had more time than I thought we would have. We got through some other stuff more quickly than we have in the past, so this is very good. So we have this one section which is kind of out of place, and since it is kind of out of place, I'm not going to put it on the test. I have not put it on the test. And I think that is it for announcements. Anybody have any questions? Okay. Then, in the event that there are no questions, I will start to go over the homework. So we have 2 homework exercises today. I have 2, I think, submissions. I have one from James and I have one from Benjamin. Benjamin is not yet here. So, James, would you mind doing? Canterbury's here. James, would you mind doing the first exercise?
Yeah, I'd love to.
You would love to. Okay, great. Let's plug in. We'll take a look. bigger. Okay. Yeah, and so I had an example. This is, now I'm remembering, this is based on some example. Yeah, okay. So we have an example. I'm not going to be able to highlight it because I don't have the PDF up. What I have is the video. Okay. So we have a set of three elements, A, B, C. Okay, you see here. And then a function whose domain is set and whose codomain is the power set of A. Okay. And so I have to find the function this way. F of A is so the inputs to the function f are elements of the set A, and the outputs of the function f are subsets of the set A. So the inputs and outputs are of a different character. And I defined this particular function this way. F of A is B comma C, F of B is the empty set, and F of C is A comma B comma C. And the first exercise, as we see on the screen here, is for the function f above, this function. What are the values of x for which x belongs to f of x? So James, how did you answer this?
So I have given f f from A to power sets of A. We know that x is an element of A, and f of x is an element of power sets of A. Since power sets of A represents all the subsets of A, it is an element of A. Therefore, f of x is an element of A.
When you say it, what do you mean by it? What is an element of A?
A is the domain of the set. No, A is the domain of the function.
A is the domain of the function.
And power sets are the codomain of the function, right? That was given
Right.
the example.
Right.
Yeah. So, yeah, I said A. Yeah. So since f of x is an element of A, and x is an element of A, as long as x is an element of A, x is an element of f of x.
Okay, so we have some misunderstanding here. You have said f of x is an element of A. Okay. Now let's go back to the video. In other words, yeah, and let's be even more careful. You are saying, regardless of what element of A I select, f of x is an element of A. But we see this is not true. For example, when we look at f of A is B comma C, and B comma C is not an element of A. The elements of A are only A, B, and C. So it would not be right to say that f of x is an element of A. We could say f of x is a subset of A. That would be an okay statement. But we could not say f of x is an element of A. That would not be correct.
Okay.
Let's see.
Yeah, I was kind of confused on the first one, on the first part of the first.
Okay. Let's take a look at, I see Canterbury is here now. Is Benjamin there? It's hard to see the front.
Oh, no. Oh, there he is. He's here.
He is here? Good. Okay. Benjamin, I have a homework submission from you. We're going to pull it up. Your timing is impeccable. Oh, but you don't have exercise 1. Okay, so we have no solutions to exercise 1. Okay, let's go back to the video. The question is, we have this function f. The question is, what are the elements of A for which, what are the elements x of A for which f of x is an element, or excuse me, for which x is an element of f of x, okay? So, in other words, let's first address the question for A. Is A an element of f of A? Who can answer this question?
What was the question?
Is A an element of f of A?
No, it's not.
No, it is not. Yeah, why not, Alex?
Because f of a is the set BC,
Yeah,
which
very
is a
good. Very
subset
good.
of A.
Very good. It is just that, okay? F of A is B comma C, so the question of is A an element of F of A is the same as is A an element of B comma C. As Alex said very correctly, A is not an element of B comma C, therefore A is not an element of F of A. Now, same question for B. Is B an element of f of B? Can someone else answer this question?
No, because the output of f of b is empty set.
Good. Nothing is an element of f of B. So in particular, B is not an element of f of B. Good. Now, is C an element of f of C? Can I get a third
Yes.
person to answer this question?
Yes.
Daniel, did you say it?
Yeah, I said yes.
Good. You said it correctly. C is an element of f of C. F of C is A comma B comma C, and C is an element of that set. So C is an element of f of C. Okay. It is important that we understand this notion because we're going to make use of this notion when we discuss Cantor's theorem in a few minutes. Cantor's theorem is a difficult thing to understand because you are addressing questions like this one we have just addressed, right? This is kind of a weird thing to think about as we are appreciating, right? This is a weird thing to think about, and so we have to just take a moment to appreciate what is the nature of this question and how do we think about answering it, okay, which we have done now. So hopefully this makes sense. Does this first exercise now make sense to everybody? How do you think about it? An element belongs to its output, x belongs to f of x. Okay. Good. Then, all right, Benjamin does have a solution to exercise 2. We will now look at it.
Isn't there another part of the first question where it's like create
Oh,
g of
yes,
x and
yes,
h of x?
excuse me.
And also,
Excuse me. You're right.
I'm still not sure for what values of a would that be like? Do you just
Well-
want like just c? Is it like just
C. Exactly right.
Oh, I thought you want like a generalization of like the question. I was confused.
Yeah, no, I don't want a generalization. The point of the homework was this statements of this type are kind of tricky, and so I don't want to deal with general statements yet. I want to deal with specific statements, just so we can try to get our head around it, and then to move forward from there. So we said, as you observed, that A does not belong to f of A, B does not belong to f of B, but C does belong to f of C. So therefore, we could make this statement. And notationally, it might look a little messy, but we will agree on the statement. The set of elements x in A such that x belongs to f of x is C. This is a statement that captures these statements. The only element x in A that belongs to its output under the function f is C. Yes, now as James reminded us, there is a second part to the question. The second part to the question is, could you construct a function f different from the one that I gave? Could you construct a function f such that x is an element of f of x all the time? Could anyone do that? Go ahead, James.
I did it.
Go ahead.
So basically, let me just unmute myself. Okay. I have let g of x equals x and h of x equals negative x, where the domain of the x value will be all natural numbers. So for all x is, as long as x is an element of A, which is the natural numbers, it is an element of g of x, which is still the natural numbers.
What you're saying, okay, so now what you're saying is not clear. You're saying g of x equals x, right?
Yes.
Okay. So you say that x is a natural number, right? This is your starting point? Okay.
Yeah.
So then if you're going to say that, then now you're saying that the output for the function is also a natural number. Okay?
Yeah.
So the output for this function is not a set. The output for this function is not a set. I want us to kind of work within, you're constructing, your function g is a function whose domain is the natural numbers and whose codomain, or range, in fact, in this case, is also the natural numbers. Okay? What I'm looking for is something like what we did even with the same set in the first exercise, okay? Where you have a set, where you have a function, f or g or whatever, whose domain is some set and whose codomain is its power set. So that the output of the function is a set, not a number. Okay, because only if the output of the function is a set does a statement like this make any sense, right? Like if I said to you, is this statement true or false, right? You would say, I don't even know how to answer true or false, that's a meaningless statement. Okay, neither of these things are even sets. So how would you say that one is an element of the other? It's not a meaningful statement. Okay, so similarly, this is not a meaningful statement if f of x is not a set. So this notation is not good. Okay. But now, James, we can stick with you. Okay, we can stick with you. Okay, we're going to go with the same framework that we had for the first part of the exercise. Okay.
Do you just want to create specific example, like f of a would be like something like that, instead of like having an actual function?
Right, exactly. So go ahead and do it, James.
Wait, what? Sorry, I got caught. Oh, okay. So f of a. Wait, what do you want me to do?
I want you to create a function, and to create a function in this case means just to define these three outputs. These three outputs should be sets, and they should be sets such that x belongs to f of x for every x in A.
Oh, x belongs to f of x. A equals the set of A and B equals set of B and C equals set of A and C.
Great, perfect.
Oh, I gotcha. So for the question, it will be g of x equals like A and B, and h of x equals an empty set. And then x will be, like the domain will be A and B. So for all value of the domain, it would be an element of g of x. For any element, it wouldn't be an element of the h of x because it's an empty set.
Maybe I understood. Let me just make sure. I heard you say H of V is the empty set. And then
No,
what did
I
you
said
say about-
I said H of all, H of anything is empty set,
Yeah, great. That's fine. That's a function.
and then
Perfectly good function.
and G of G and suppose we have A equals the set of A and B. Make it simpler. Then we have G of A equals G of A equals the set of A and B, and G of V equals the set of A and B, and we don't have any
Yeah,
H's.
exactly. Very good.
So that
Very
way-
good. Very good. I like your solution. I like your solution. There's beauty in simplicity. He made the simplest solution. This would be the simplest solution to the exercise. This is also a solution to the exercise that he gave here to a part of the exercise. So this is very good. Good. Okay, good. That was good. We went from not understanding to understanding. That is a beautiful thing. That is a beautiful thing. So very good. Okay, so now we understand what these statements must look like. Okay. Very good. So let us thank James for his work on this exercise. Very good. Okay. Now exercise 2. We are ready now to come to Benjamin. He has a solution to this exercise. Last exercise. I don't know how many total exercises there are in the course, but this is the last one. Okay, so yes, this is the question where you are supposed to make some sort of argument that if you have a finite set, the power set has more elements than the set, basically. So Benjamin, take it away.
So, inside the power set, for each item in the set A, there is always a single element set such that your function, which is f of x, is the set x. But in addition to those sets, there's also the null set and possibly other sets, since each item in your original set has a single element item in your power set, and there's additional sets. There can not be a bijection from A to P of A.
Okay, how do we feel about Benjamin's argument? He's saying for every element in your set, that element corresponds to a certain subset in the power set, but then there are other excluded elements, including the null set, as he said. There is one, it is largely a good argument. There is one small oversight in the argument. Does anybody see it? Very subtle. Very subtle oversight in the argument. Do I have any thoughts on that?
But if I was thinking if A is a set of if A only has one element, then the power sets will be the one element and the empty set. Would the empty set count as like one in cardinality, or it doesn't? If it doesn't, then it'd be the
Well,
same.
the empty set, it doesn't contribute one. It contributes one to the cardinality of the power set. It doesn't contribute one to the cardinality of the set.
Yeah, I think this is correct because as long as you have the domain as it contains at least one number, then the power set would always be larger because it would contain the empty set as well.
Yeah, actually, as I review his argument, I think if I read it a certain way, I could understand it to be a good argument. The thing that makes me a little squeamish about this argument, and in general, when people present arguments about sets, it is an easy thing to overlook. And so this is always something when you're analyzing an argument that someone makes about something involving sets. This is the sort of thing you want to look for. very subtly, he says this, which I failed to highlight. For each x in A. Okay, now, this seemingly innocuous clause contains in it a certain little assumption, depending on how you read it. Depending on how you read it. So this is where I am saying I could interpret this a couple of ways. To me, as I read it the first time, this statement implies to me that the set A is not empty. Okay? Because you're saying that I can take elements from the set A for each x in A. Okay, so now maybe you might in return say, well, you can do this for each x in A provided there is an x in A, and this would be a reasonable adjustment, but it's a little bit unclear, and it looks a little bit like making an assumption that the set contains elements, okay, which in general you don't want to do. And there are lots of statements about sets that can be made that appear to be true, but then are not true because the empty set is a counterexample. So you have to be aware of the empty set all the time. Okay. Yeah, and then if the set is empty, then this statement again is a statement that I have to understand how to interpret. Are you saying that there are no sets in the power set? Or are you saying that there are sets in the power set of this type? Because if the set is empty, it contains no sets of this type. But you can say, well, that goes back to the earlier implication that you should do this only when possible. Okay. So in any case, I would just say the ideas are all here, but it should be polished a little bit. It should be polished a little bit.
Well, I could reword that.
Pardon me, Benjamin, I didn't hear you.
I could reword that as there's an equivalent number of single element sets as there are elements in A.
Well done. Yes, this would be very good. And in addition, it contains the empty set. Yes, let's remember, if A is the empty set, it has no elements. How many elements are in the power set of the empty set?
1.
1. Namely, the empty set. Okay? The set of all subsets of the empty set is the empty set. The empty set is a subset of itself. Every set is a subset of itself, including the empty set. And the empty set is a subset of every set, including itself. Okay, so if we just if we agree to understand this, thinking about the empty set in a certain way, then I agree that we have a good argument. But we have to make sure that we are accounting for the empty set well.
Dr. Phipps.
Yeah, and you can also make an analytical argument. You can also make an analytical argument based on some results that we know.
Dr. Fitz?
Yes, excuse me, go ahead.
Yeah, that's right. If A is an empty set, and P of A is an empty set, wouldn't there theoretically be a bijection between the two?
If A is the empty set, P of A is not the empty set. P of A is the set containing the empty set. So that's kind of a weird thing to think about. If A is the empty set, then P of A is the set containing the empty set. Okay. The power set of a set is always, okay, so I'm going to use the word set like 8 times in one sentence, but the power set of a set is a set that consists of sets. Okay, so just like here, if A is ABC, as we saw in the reading, right? The power set of A is a set whose elements are sets. Okay, namely the empty set A, the set B, the set C, set AB, set BC, set AC, and set A, B, C. Okay. So it is a set that whose elements are sets. A set whose elements are sets. We see that there are 8, counting them. There are 8 subsets of the set A. Okay. there is one subset of the empty set. That set is the empty set itself. Okay. So the power set is the set containing the empty set. So that's a weird, seemingly a weird statement to make. But if you just remember that the power set of a set is the set of all its subsets, then it makes sense, right? What are all of the sets that are a subset of ABC? I can just list them, okay, which I did. What are all the sets that are a subset of the empty set? I can list them. There is one. There is one set that is a subset of the empty set. And therefore, the cardinality of the power set of the empty set is 1. Because there is one set that is a subset of the empty set. Okay. Now, something that we have seen earlier in the course, and we saw it a couple of different ways, okay, is that if a set A has n elements, and this is a way that we write that sometimes, cardinality, we kind of use these absolute value symbols, okay? Then, how many elements does its power set have? Who remembers this? Something we've seen many times.
Two to the n?
2 to the n. If a set has n elements, that set has 2 to the n subsets, as we see here. Set A has 3 elements, P of A has 8 elements. Okay. So then the question is basically, is the power set always bigger? That means the question basically reduces to this question. Is this true for all natural numbers n and 0? Some people include 0 as a natural number and some don't. Okay. And then now this is a question you can resolve using some analysis. Okay, using some. I would think to use calculus. I would think the question is equivalent to this one. Okay. Is this statement always true? And then I would think of this as a function of n, and I would say if f of n is 2 to the n minus n, then f of 0 is positive, and f prime of n is also always interesting. Yeah, I guess I have to be a little more careful. F prime of 0 is, I want to say it's increasing, right? My plan is to say the function is increasing so it never takes a negative value. But the function is not increasing all the time. In particular, f prime of 0 is not positive, right? You get ln of 2 minus 1, that's negative, okay? But I can also observe that f of 1 is also 1. F of 1 is also 1. And f prime of 1, f prime is positive and becomes more positive, okay? So the function does not have negative values for small values of n, and then the function continues to increase. So therefore, this expression will never be negative, and that implies that this is true. So you can apply analytical methods also. I like the argument with non-analytical methods. I just want, so what Benjamin presented I like very much. But also I wanted to make you aware of the fact that there are other ways you can view solutions. Okay. Does anyone else see me changing colors?
How are you changing color?
Yeah, like now I look kind of red, and then I was blue.
You were
There you go. You all. There's a very loud thing in my school. I don't know what happened, but maybe some wires are loose or something. I'm changing colors. Okay, sorry. There was a question. Who was it who had a question?
I had a question. Could you also graph it to prove, could you just show the graph of 2 to the n minus n to prove that,
Yeah, this is good. In general, you know, something your geometry teacher would tell you that I would also tell you is that a picture is not proof, right? So you would want to say a little, I mean, the graph will indicate that in whatever window you're looking at, the function never attains a negative value, but then you should comment in some way like why the pattern that you see in the graph continues. It's pretty clear that it continues, but you should comment something. Yeah, but that would be a good tool, right? A graph is a good tool as well. Okay. All right, let's thank Benjamin. You did a great job. Okay. Now, this shows that whenever you have a finite set, its power set is a bigger set. Okay. Meaning it has more elements. Okay, the set has more elements. A natural follow-up question is, if you have an infinite set, is it true that the power set of an infinite set has a different cardinality than the original infinite set? Like, or in other words, is the power set a bigger infinity? Is there a greater infinity of elements in the power set than there is in the original set? Okay. First of all, let's appreciate what this would mean if true. Okay. If it were true that a power set had was corresponding to a bigger degree of infinity than the original set, then this would tell us something about how many infinities there are, right? Because let's say I start with the natural numbers, right? Let's say I start with the natural numbers. Well, what this would tell me is that the power set of the natural numbers is a bigger infinity, so uncountable in particular. But then, if I took the power set of that power set, I would get an even bigger infinity. So this is even more than uncountable. I mean, uncountable just means more than countable, but it's even more than this particular uncountable set. We wouldn't have a word necessarily for that, but it would be a greater infinity. And then if I took the power set of that set, it would be a greater infinity, etc. Okay, so if the statement is true that the power set of an infinite set is a greater infinity than, or greater in cardinality is the more precise way to put it. If the power set of an infinite set is greater in cardinality than the original infinite set, then this implies that there are infinitely many levels of infinity. Okay. So that's what this result would mean. It seems like the result may be true. We can prove it in the case where the sets are finite. To prove it in the case where the sets are not finite, and I started to look at what Benjamin sent me. I think Benjamin was doing something in this direction. But I didn't read it very closely. Maybe we'll take a look at it if we have a chance. But Cantor's theorem says the following. There is no bijection from A to P of A. So very simple. So in other words, this result is just generalizing what Benjamin proved in exercise 2 for finite sets. There is no assumption here that the set A is finite. Okay, so this result, as we remarked a moment ago, is going to imply that there are infinitely many different levels of infinity. Okay. All right. Proved. The proof cannot take the same form as the previous proof because we can't work with the number of elements in the set, so we have to do something different. And the something different that we have to do is to think back to exercise 1. We're going to need to construct something that is of the flavor of what we looked at in exercise 1. Okay? So the proof is by contradiction. Suppose that such a bijection exists. And we will call it F. Okay? So we're supposing that this function F is a bijection from the set A to its power set. Then we let B equal the set of elements of A such that x does not belong to f of x. So it is a set just like we were thinking about in the first exercise, okay? For every element in A, for every element x of A, there is a corresponding element of P of A, which is the output. I put some element x from A into the function. I get some output, which is a set. And then I can ask the question of, is the input an element of the output? Just as we did in exercise 1, which we all understood at some point. And so now the set B is the set of all the elements of A where the input to the function is not an element of the output. Okay. So in exercise 1, this would have been A comma B. In exercise 1, what we saw was C was an element of f of C, but A was not an element of f of A, and B was not an element of f of B. So in exercise 1, this set would have been A comma B. Okay. All right, any question? Everybody okay so far? Does this make sense? Same sort of setup. Okay. Now is where we use the fact that we have a bijection. Okay, so since the function f is a bijection, this well, okay, so I should go more slowly. Okay. The set B is a set containing elements of A. Okay. So since the set B contains elements of A, this means that B belongs to the power set of A. B belongs to the power set of A. It is a subset of A, right? And the power set of A is the set of all subsets of A. All right. So therefore, since the function is a bijection, what we know is that every element of the codomain is attained, right? Every element of the codomain is attained by the function for some input. Okay, so in other words, what this implies is, since f is a bijection, there is some y in A such that f of y equals b. This is just because this is what it means to be a bijection. Every element of the codomain, every element of P of A is the output for some input from the set A. Okay. So then we ask the question, and then once we start to think about this question, then we realize that we have the result. The question is this. We know that B is a set of elements of A. We know that y belongs to the set A. So the question we ask is y an element of B? This is the key question. Is y an element of B? Well, what would it mean? If y is an element of B, then by definition, what is the defining characteristic of the set B? Set B is the set of all elements that don't belong to their output under the function f. So this means by definition that y is not an element of f of B. But what is f of B? Or excuse me, y is not an element of f of y. Excuse me. That's the definition. Y is not an element of f of y. Okay. So now what is f of y? Look around you at the board and you might see it. What is f of y? It is b. Good. F of y is b. Okay. So this would imply that y is not an element of f of b. Right. F of y is b. So if y does not belong to f of y, then y does not belong to b. So this is a contradiction, right? If y belongs to B, then that implies that y does not belong to B. So that can't happen, right? So this possibility is not possible. Now we think about the other possibility. What happens if y does not belong to B? Well, again, if y does not belong to B, by definition, B is the set of all elements that don't belong to their output under the function f. So if y does not belong to B, then that means that y does belong to f of y, by the definition of the set B. And f of y again is B, so this implies that y belongs to B. And so again, you have a contradiction. Neither situation is possible. Okay? We see that if we assume that y belongs to B, that can't be correct. And if we assume that y doesn't belong to B, then that can't be correct. So that means that y is nowhere, and we have a contradiction. Okay, now we have a contradiction. And so this means, as usual in a proof by contradiction, that our original assumption cannot be satisfied. Our original assumption that such a bijection exists cannot be satisfied. Okay. Any questions? So this proves that this proves the theorem. This proves that there's no bijection from a set to its power set, and so this addresses a question that you may have had a while ago, right? We learned a while ago that not all infinities were the same, that the natural numbers were countable and the real numbers were uncountable. Okay, we proved that. But then you might have said, is there any set that is bigger than the real numbers? And the answer is yes, the power set of the real numbers is bigger than the real numbers. And the power set of the power set of the real numbers is bigger than that, etc. So there are infinitely many infinities. Interesting result. Okay, Benjamin, would you mind just, you sent me something which you called an exercise 3. What was that about?
You mentioned that you wanted someone to prove something like this. So I was trying to prove it, but I only proved it for a countably infinite set.
Gotcha. Okay, nice. Yeah, I'm looking now at your result, and I need to look at it more closely. I'm not going to be able to think through it in the next 10 seconds, but I'll give you some feedback on that. But it looks nice. It shows you have learned some things, or you had already, hopefully, learned some things this semester. That would be good, but maybe you knew them already. So it looks very good. Okay. Any questions? All right, then if there are no questions, I don't know when I'll get to see you guys again, but I hope to see you guys around sometime. It's been fun for me. I hope you enjoyed the class. I hope you learned some stuff. If you have any questions between now and your test, be in touch. And I wish you all the best. I wish you all the best, and I'll see you guys around. Take care.
All right, thank you, Dr. Fitz.
Thanks, Dr. Fitz.
Thanks, Dr.
Thank you,
Fitz.
Dr. Fitz. See you guys.
Bye.
Bye.